Okay, maybe we should start right now. Now it's already 11:02. Okay, and good morning, everyone. Today we will continue planar kinetic equations of motion. And I will briefly review what we did last Friday, and then start with two examples. Now, in these two examples, the first one, I'll show you that how we use planar kinetic equations of motion in general motion. That means we consider both translational as well as angular motion. How we use planar kinetic equation of motion to find internal forces. That's the example 24. Example 25 is how do you use the same approach to determine the reactions or to determine the maximum force in a dynamic loading situation. So that will be example 25. Then after these two examples, we will move on to kinetic energy, which actually I talked about it very briefly before, but I will take this opportunity to also review and show you the connection of this part to the framework that I have been talking about so far. Okay, let's get started. Example 24. In this example, we have you can call it wind turbine blade, or you can call it a fan blade, but it's basically a fan system. In the fan system, we have few points identified. Point P, point O. So the center is, of course, right here, this point is called point O, and the connection between the blade and the centerpiece is called point B. The top point is called point B. The down point is point A. Now, this fan is subjected to angular velocity, omega, to be 6 radians per second, and is also subjected to an angular acceleration, alpha, to be 5 radians per square second. Dimension-wise, we also know that from point O to point P, this is 15. What I use? Millimeters. So it's really a band. From point B to point P, and this distance is 300 millimeters. Now, what's the question? The question is, when the fan is in this orientation, we want to know that what will be the forces developed between the blade B and the centerpiece. That's the question. Because when we cut it here, you can move this part to something like this, and you will know that the blade can be cut into something like this. Move this thing a little bit lower, right? Once we cut it into two different pieces, you will know that at the interface, we're going to have forces developed at the interface. We're going to have the normal force, right? And besides normal force, you also have shear force. And besides the shear force, we also have what? We also have moments, right? So there's also moments developed right here. So this is at point P, of course. And that's what this question is about. And first of all, why there will be internal forces developed at point P? That's because in angular motion with subjects or objects with sizable geometries, angular motion will produce what we call centrifugal force. And the centrifugal force, depending on the geometries, could actually result in not just normal force, but also shear force and also bending moment. That's why when you start spinning something, there will be internal forces developing. Example 24 is to exercise the principle from planar kinetic equation of motion to figure out how we can determine these three internal actions or reactions. The perpendicular one, we will call it normal force. So maybe we call it normal force P and P. And the horizontal one, you may call it shear force, VP. Subscript means that the force at point P. Of course, then the moment here, we call it MP. Then this problem is about finding the three of them. Find MP, VP, and MP. And of course, you need some information. And the information is the mass for the blade. So we call it mass of the blade. And from P to B is 2 kilograms. And you also have the mass moment of inertia at the center of gravity for this blade. And suppose the mass moment of inertia at the center G, and center is right here. So the mass moment of inertia for this blade, PG, is also given. And this is 0.18 kilogram square meters. So that's the information we have. Okay. Now, how do we solve the problem? First of all, you know that in order to determine the force equilibrium, you remember the difference between angular motion and linear motion is this. In linear motion, when we set summation of force in a certain direction equals to that summation, the product of mass times the resultant acceleration in a given direction. We know this is linear motion, right? And in angular motion, the same thing. The summation of all the moments in a certain direction must be equal to all the forces and the moments produced here. In linear motion, we have this to be 0. So this is the governing equation in linear motion because there's no angular, what we call what? Angular inertia or mass moment of inertia, right? So this is the governing equation for linear motion. For angular motion, summation of the forces equals to what? Equals to not only this, but there's also another component coming from angular, what? From angular motion. Therefore, the angular motion will result in different components contributing to the linear acceleration. And that is on my notes, so let me put this together. So you would be able to link these two together.